Good afternoon to all of you. The topic which I'm going to discuss is organometallics and fluxionality and organometallic compounds. Organometallic chemistry is a vast branch of chemistry that bridges the gap between organic and inorganic compounds. When we talk about organometallic compounds, the term organometallics basically comprises of two things, organo and metallic. The organo means it belongs to something that is made up of carbon, and metallic is any metal. So when metal and carbon, they're directly bonded to each other, such compounds, they are known as organometallic compounds. This carbon can be of any nature. It can be alkene, alkyne, allyl, aryl, and so on. Any carbon compound that can be bonded with metal carbon atom. And the metal can be any of any group. It can be of alkali group, alkaline earth metals, it can be transition metals, it can be your post-transition metals. Depending on the metal which is bonding with carbon, the bonding can be ionic, covalent, localized or delocalized in nature. Now we will classify the organometallic compounds on the basis of types of bonding between metal and carbon. First one is ionic organometallic compounds. In these compounds, as the name suggests, the bond between metal and carbon would be ionic in nature. Okay, so if metal and carbon, they want to form an ionic bond, that means there must be some electronegativity difference between them. That is why they will exist as cations or anions, or there will be some charge separation between them. So if the charge separation needs to be there between metal and carbon, the metal should be highly electropositive in nature. That is why the most electropositive metals of group 1 and group 2, when they combine with carbon, they form the ionic organometallic compounds. These are the common examples like sodium ethyl or your cyclopentadienyl that combines with sodium ion. So sodium is your group 1 element, that means it's highly electropositive. When it combines with the electronegative carbon atom, there is a charge separation, and that is why an ionic organometallic compound is formed. The next one is covalent organometallic compounds. Covalent organometallic compounds means the bonding between metal and carbon will be covalent in nature. As you all know, the covalent bond gets formed when there is equal sharing of the electrons between the metal and carbon. So if there needs to be equal sharing, that means the electronegativity difference won't be much. So that is why when the carbon gets bonded to group 13, 14 and 15 elements, then the formation or generation of covalent organometallic compound takes place. These are the common examples. As you can see, this tetramethylsilane, here the bond is between silicon atom and your carbon atom. So they almost have the similar electronegativity. That is why equal sharing of electron is there. So a covalent organometallic compound is formed. Similarly, the other examples shown here, there are the examples of covalent organometallic compounds. Next one is your electron deficient organometallic compounds. Electron deficient organometallic compounds are formed between your electron deficient elements. When they get bonded with your carbon atom, the electron deficient organometallic compounds get formed. So electron deficient means they don't have your full octet even when they form bonds. Like you can take an example of BH3. When boron get bonded with 3 hydrogen atoms, still its octet is not complete. So BH3 is electron deficient compound. Okay, so the elements of this family, boron, aluminium, they form the electron deficient compounds because they have lesser number of electrons. So as they're electron deficient in nature, so they have a tendency to associate strongly and form polymeric structures. So most of the electron deficient organometallic compounds, they will exist as polymers or dimers due to the deficiency of electrons. Okay. And then last one is transition metal organometallic compounds. As the name is suggesting, transition metal organometallic compound is formed when a transition metal gets bonded to carbon. Okay, so the transition metal can be of any group. It can be of 3D series, 4D series or 5D series. When the direct bond formation is there between your transition metal and the carbon atom, there will be the formation of transition metal organometallic compounds. The ferrocene is a very common example. The first one is Zee's salt. There is a direct bond between platinum and this alkene. The next one is ferrocene. Iron is bonded with the carbon of cyclopentadienes. That's this one, dibenzene chromium. Here chromium metal is bonded with the benzene group. Okay, so these are the transition metal organometallic compounds. Next concept which comes is hapticity. We are talking about the organic ligands. There can be one carbon atom, there can be two carbon atom, three carbon atom, and the metal can bond with any number of carbon atoms depending on the presence or availability of electrons. So we have denoted a term hapticity. This is represented by eta. Hapticity is basically the number of carbon atoms of the ligands which are attached to the metal atoms. That will be your hapticity. We will discuss some examples. For example, if your hapticity is 1, that means the carbon atom of the ligand is bonded directly to the metal. One carbon atom, when one carbon atom is directly bonded to the metal, the hapticity will be 1. For example, in the first figure that is shown here, metal is only bonded with one carbon atom. It is not bonded to other C2 and C3 carbon atom. It is just bonded at C1. So metal is bonded to only one carbon atom. That is why hapticity is 1. In all these examples, when metal is bonded with one carbon atom, hapticity will be 1. Similarly, if we talk about two carbon bonded ligands, metal will be bonded with two carbon atoms of the same ligands, and the hapticity will be known as 2. Common example is your alkene. In alkene, there is a pi bond that is equally shared between two carbon atoms. So when metal gets bonded to, or metal share this pi bond, that means it is bonded to both the carbon atom. So that means hapticity will be 2. Next one is 3 carbon bonded ligands. In the eta allyl is the common example. When the metal is bonded with the 3 carbon atoms, there is a resonance between these allyl group. So if you talk about this resonance stabilized structure, when the electron cloud is over all the 3 carbon atoms, the metal that is bonded to all the 3 carbon atoms. So these are named as triactal ligands because metal is sharing the pi electron cloud of all the 3 carbon atoms. Next one is 4 carbon bond ligands. When metal is sharing the electron cloud that is circulated or spreaded over the 4 carbon atoms, the hapticity will be 4. The conjugated diene is a common example. Similarly, eta 5, eta 6 and eta 7 organometallic compounds are there depending on the number of the carbon atoms that are bonded to your metal atom. Okay, this is the concept of hapticity. Next one is effective atomic number rule. Effective atomic number rule, as you must have studied in your lower classes, there is an octet rule. So what does octet rule states? It states that any your element or any state that will be stable if its octet gets completed. Okay, that is for p block elements or your lower elements. But when the electrons are getting filled in the d orbitals, we talk about 18 electron rules because S, P and D. S has 2 electrons, P can accommodate maximum of 6 electrons and D can accommodate maximum of 10 electrons. So 2 plus 6 plus 10, that is equal to 18. So from there the 18 electron rule or effective atomic number rule comes. Okay, so when you talk about the most common organometallic compounds of the transition metal, the stability of any organometallic compound is basically decided by the effective atomic number rule. For example, this CrCO6, chromium is bonded with 6 carbonyl ligands. So why only 6 carbonyl ligands are attached? Why not 5, 4 or 3 or more than 6? Because chromium is atomic number 24. Okay, and the nearest noble gas configuration would be of your xenon. So if 6 terminal groups are attached to chromium, that means 12 electrons will be given and that will make the total of your 36. 36. Okay, and this 36 is the noble gas configuration. Sorry, I said earlier xenon. It is of krypton. Krypton has atomic number 36, and this is noble gas configuration. That means it's all 18 electrons are filled up. It doesn't have any lesser or more number of electrons in its valence shell, and thus effective atomic number rule is followed. So if the total number of electrons possessed by the central metal ion plus the number of electrons gained by it from the surrounding ligands achieve the same atomic number as the next noble gas, the compound is known to follow effective atomic number rule. And the number of ligands which are getting attached to any metal, it basically depends on whether it is following the effective atomic number rule or not. Okay, let us consider another example of FeCO5. In iron has atomic number 26, so 26 electrons are there in iron. Each carbonyl ligand will donate 2 electrons. So if 5 COs are there, that means total of 10 electrons will be there, making it to a total of 36. So 36 is a noble gas configuration. It is atomic number of krypton. So that is means the effective atomic number rule is obeyed. Similarly for MoCO6, molybdenum has atomic number 42. So 6 terminal groups are there. So 12 electrons will be donated by the ligands, making a total of 54. Okay, so this is also a noble gas configuration. That means your effective atomic number rule is followed. Okay, so on the basis of effective atomic number rule, we can also predict the type of bonding that will exist in an organometallic compound. For example, in this Fe3CO12, there are 3 iron atoms. That means 3 into 26, it will donate 78 electrons. 12 CO groups, that means 12 into 2, it will give you 24 electrons, making it a total of 102. I have written by mistake as 72. The total will be 102. Since there are 3 iron atoms, that means if you count the number of electrons per iron atom, that will be 102 divided by 3, that is equal to 34. So in order to follow effective atomic number rule, it should have 36 electrons, but it has 34 electrons. So that means each iron atom will be bonded with 2 more iron atoms so that it gets its count to 36. So that's why this structure is CO12. There are 4 cobalt atoms. That means 4 into 27, total of 108 electrons will be there. 12 CO ligands. So each ligand will donate 2 electrons, making it to a total of 24 electrons. So the total electrons will be 132. And if you count the electrons for individual cobalt atom, that will be 132 divided by 4, and that is equal to 33. So in order to follow effective atomic number rule, it should have 36 electrons. That is why each cobalt atom forms 3 cobalt-cobalt bonds to follow the AN rule. So with the help of AN rule, we can also predict the structure of the organometallic compounds. Next one is, these are examples which show your effective atomic number rule is obeyed in these examples as well. These are your heptal ligands or organic ligands. This is pi C3H5. That means pi allyl group. All the heptal ligands, they will donate the number of electrons on the basis of their hepticity. Pi allyl means there are 3 electrons, or the metal is bonded with 3 carbon atoms, so it will donate 3 electrons. Okay, similarly in the lower next example, the ligand is pi C5H5. Okay, that means it has hepticity of 5, so it will donate 5 electrons. So the number of electrons that are donated by the ligand depends or is equal to the hepticity of your heptal ligands. So in case of heptal ligands, your number of electrons will be equal to the hepticity, and in case of your neutral ligands, the number of electrons shared will be equal to 2, and if you have anionic ligands, the number of electrons shared will be equal to 1. So with this, you can count the number of electrons present in your compound. Next topic is fluxionality in organometallic compounds. Fluxionality basically means that the non-equivalence of two or more structures that can exist in the molecules with different instantaneous identities. For example, you must have heard about the ketone tautomers. They can easily change from one form to another, but they have different property. One is ketone and another is alcohol. So they have different chemical structures and different chemical properties. But if you talk about fluxionality, the chemical properties of a fluxional compound is same. Okay, it is just the rotation of the one part of the molecule with respect to another, and it gives different form of the same molecule, and they have same chemical properties. Okay, so tautomers means, like I told you before, tautomers means your chemical non-equivalence is there. One is alcohol, one is ketone, so they are chemically non-equivalent. But the fluxional molecules, they are chemically equivalent. If you talk about this ammonia, they have different spatial arrangement, okay, but their fluxionality or their chemical nature is same. You cannot differentiate between these two structures on the basis of chemical properties. They are chemically equivalent to one another, but yes, their spatial arrangement is different. So fluxionality is just the rotation of one bond from one place to another. The common example is this trigonal bipyramidal geometry. It get transformed to square pyramidal geometry. Then after the rotation, it again get transferred to trigonal bipyramidal geometry. So this is a common example. This is known as Bailey pseudo rotation. Okay. It causes molecules of certain geometries to isomerize by exchanging the two axial ligands. The two axial ligands, they are getting isomerized with the two of the equatorial ones. So these are, but all these structures, all these organometallic compounds, they are chemically equivalent. It is just the exchange of the ligands in these molecules, and this phenomena is known as fluxionality. Okay, and why does fluxionality happens? Why the electrons, why the bonds they are getting exchanged? Because the energy difference between the trigonal bipyramidal and square pyramidal geometry is very less. So flexibility is easily changed due to strong vibration. If they're getting strong vibration, they will be flexible and the bond can be interconverted from the axial to equatorial. So that is why, due to lower energy difference between the two geometries, the fluxionality is possible. So how can we determine whether a molecule is showing fluxionality or not? We can determine it on the basis of NMR spectroscopy. At the lower temperature ligands, lower temperature limits, there will be no rotation in the bonds, no vibrations in the bonds. So that means the equatorial bonds will be fixed and the axial bonds will be fixed. So you can determine whether which of the ligand is at equatorial position and which of the ligand is at axial position. But when the temperature becomes high, the interchange between the axial and the equatorial bond is so fast that you cannot predict it or you cannot determine it using NMR spectroscopy. So NMR spectroscopy at lower temperature limits help us to study the fluxionality, but at the higher temperature limits, you cannot record the fluxionality between the molecules. This is the fluxionality in cyclic polyene complexes. If you look at this complex, iron is bonded with one CO ligand, another CO ligand, this eta 5 cyclopentadiene ligand, and another one is eta 1 cyclopentadiene ligand. If you look at the NMR spectra, at the lower temperature of minus 80 degrees Celsius, you're getting 3 peaks, and these 3 peaks are due to your eta 5 and eta 1. But at the higher temperature limits, these peaks start to coalesce, and if you further increase the temperature, the bonding or the movement between your axial and equatorial bond becomes so strong that you cannot predict by the NMR spectroscopy which hydrogen atom is there, HA, HP or HC. So you're getting a single peak at higher temperature, but at the lower temperature you're getting 3 peaks due to different cyclopentadienes. Okay, so this is the fluxionality in metal allyl complexes. In metal allyl complexes, as you can see, there are 3 different types of hydrogens. One is the central hydrogen, HC, Another one is HS. This is syn hydrogen. Syn hydrogen means it is towards the metal atom. And another one is your anti hydrogen atom. It is away from the metal atom. So there are three types of hydrogen atoms, and when you do the NMR spectroscopy at a lower temperature, you will get the NMR spectra due to all these three different hydrogen atoms. You will get three peaks, but at the higher temperature, the interchange between these syn and anti-hydrogen atom is so strong that NMR spectra cannot predict or cannot depict the difference between these hydrogen atoms. So at the higher temperature, you will just get two peaks, one due to central hydrogen and another due to syn and anti-hydrogen. But at the lower temperature, you're getting three peaks, one due to central hydrogen atom, one due to syn hydrogen atom, and one due to actual anti-hydrogen atom. So NMR spectroscopy helps us to predict at the lower temperature whether the fluxionality is present or not. This was all about fluxionality in organometallic compounds. Next one is applications of organometallic compounds. They are used as homogeneous catalyst in variety of reactions. These compounds are used as stoichiometric reagents in both industrial and research-oriented chemical reactions. They are used in the production of LEDs, in the production of semiconductors. These compounds are employed in bulk hydrogenation processes, such as the production of margarine. These compounds are used as catalysts and reagents during the synthesis of some organic compounds. And the organometallic compounds are also useful in the facilitation of the synthesis of many organic compounds. So this would be all for today's lecture. Thank you all.